Hello guys, welcome back to channel. I'm Ashkan and this is another video of Fluid Mechanics 1 tutorials. In this tutorial I will solve two problems about a linear momentum equation which is related to chapter 5 of the book. First, if you like these videos and if you find these videos, these tutorials useful, please share them with your friends and subscribe to the channel. I have lots of other videos you can enjoy and you can use to learn about CFD and drawing different plots or numerical simulations. Okay, this is tutorial 7 of the Fluid Mechanics 1 course at Concordia University. This is the first problem number 39 of chapter 5. We have this plate and we want to hold it steadily, stationary, while there is a jet of water impinging this plate. So we should find the magnitude of force required to hold the plate stationary. Here we have a jet of water with a velocity of 30 meters per second and the flow rate of 5 kilograms per second. The plate is inclined with the angle of 45 degrees. So in these kinds of problems, where we have fluid flow and we want to find the magnitude of force, we should use linear momentum conservation. So linear momentum equation or conservation. If you know, this is the linear momentum equation. The summation of forces should be equal to the change of momentum inside the control volume in time. So rho v dv, this is volume, this is velocity, plus the exchange of momentum through control surfaces. So rho v dot n dA. In Fluid Mechanics 1, in this course, we usually solve problems in a steady state, and therefore the first term is 0 when we are dealing with a problem in a steady state flow, which happens most of the time. Okay, now we want to solve this. There are some steps you have to follow. The first one is to draw the control volume. So first step is to draw the control volume. This is the control volume I pick. So if I draw it here, we have this control volume. There is no rule, but you can use the characteristics of the problem. For example, control surfaces should be perpendicular to the flow. So for example, here we have a flow and this control surface is perpendicular to the incoming flow here, and there we have two control surfaces that are perpendicular to the outflow that we have at section 2 and 3. And the other rule maybe is to follow the flow, where you have a jet or free surface or interface, and also it should be parallel to any wall that you have. So this is parallel to wall, control surface 1, CS1, CS2, and this is CS3 are control surfaces perpendicular to the flow. And we have a force. This is F. We should find it, and that's it. The first step is to draw the control volume, identify the control surfaces where you have inflow or outflow, because it's important, the direction of the flow. And then the second step is to select X and Y axis. You should define the X axis and the Y axis. Most of the time we pick the direction in which we have the force. So here we have this F, so this should be, for example, X axis, and this should be Y axis. The X axis is mostly choose in a way that it will be it is parallel to any force that you want to calculate. So step number 1, control volume. Step number 2, coordinate system. And step number 3, which is solving the problem in the direction that you want. Here we have to find the force, so we need to solve the linear momentum equation in X direction. So let's rewrite the expression. Summation of forces in X direction is equal to change of the momentum inside the control volume plus the exchange of the momentum through control surfaces. So now it's important to know that rho Vx, this velocity is velocity in the direction that you want to solve. So here you have X direction, so here you have Vx times V dot N dA. Imagine this is, for example, control surface 1. We have inflow, so this is V1. Oops, sorry. Okay, so V1 is perpendicular to this control surface and it's inward because we have inflow. N is outward normal vector. So here at inlet, we have inlet here. This is V1, this is N, and we have 180 degrees between these vectors. So V dot N at inlet is always minus V, and this V is the magnitude. because this dot product equals the magnitude of V times the magnitude of N times cosine of theta, which is 180. So this one is the outward normal vector. The magnitude is 1. Cosine of 180 degrees is -1. So for inlet, it's minus V. And for the outlet, this is V, for example, and this is N. So here, for the outlet, this is N. They are parallel. So for outlet, V dot N, it's always positive and equals to the magnitude of V, outflow velocity. Okay, let's get back here. So since we are working at steady state, the first term is 0. In x direction, we have only F. So we only have one force, F, which is in the opposite direction to the x. So minus F equals, we have three contour surfaces, but contour surface 3 and 2 are perpendicular to x. As you can see, the velocity v3 and v2 are perpendicular to the x direction, so they don't have any momentum in this direction. So the only contour surface that matters is CS1. So it's equal to, on contour surface 1, we have rho v in x direction. This is v1, and here we have x. This is y. This is x direction. Here is 45 degrees. So this is v1. So v1 in x direction equals v1 cosine of 45. So rho vx at contour surface 1 is v1 cosine of 45 degrees, and v dot n is always the magnitude, but here we have inlet, we have inflow, so times minus v1 dA. And for contour surface 2, as you know, rho vx, we don't have any v velocity, doesn't have a component in x direction, so vx for contour surface 2 is 0, but since we have outlet, v dot n is v2 dA, and for the third contour surface, it's the same, 0 v3 dA. So these terms are 0. So what we have is minus F equals rho v1 cosine of 45 minus v1, and the integral of dA at contour surface 1 is a1. So it's equal to rho v1 a1 minus v1 times cosine of 45. As you know, m dot equals rho va. So at inlet. At the inlet at control surface 1, rho V1A1 equals m.1 mass flow rate. So we have a minus here and a minus here, so they cancel. So F equals m dot V1 cosine of 45. We should use the mass flow rate because we don't know the area, but we know the mass flow rate. That's why we use this. Now you can find F as, you know, m dot is 5 and V1 is 30. M dot is 5 kilograms per second, V1 is 30 meters per second, cosine of 45. So F equals 106 Newton. Let's jump to the second question. This is the second question, problem number 59. Here we have this gate. Determine the magnitude of horizontal component of the anchoring force required to hold in place the sluice gate, this gate. So we want to find the force which is needed to hold it. For example, this one, Rx. Compare these results with the size of the horizontal component of the anchoring force. Oh, sorry. When it is closed and the depth of water upstream is 10 feet. So we have two situations. In the first one, situation 1, the gate is closed. This is the gate. Here is the water surface. The depth is 10 feet. And there is no flow. And in the second situation, we have the flow. Like this. This depth is 1.5 feet. This one is 10 feet. And we know the velocity, which is 4 feet per second. So we want to find Rx in these situations and compare them. Okay, let's start with the first situation. Here we don't have any flow. So if you want to define the control volume, it should be like this. Follow the free surface, the wall, and here, and go up. Here we don't have a inflow. Okay, that's not a problem. So for this, actually it's fluid static and you know how to find the force. Here is Rx. Because of this column of water, we have this force here, Fr. And since there is no flow, you can use fluid static formulas. You know Fr equals gamma hc times area. We know the liquid is water. Hc, since it's a rectangular gate, is depth divided by 2. So hc equals 5 feet. And the area, we don't know the width of this gate, so we should solve it. let me see. Yeah, we should solve it per, we should find the force in pounds per feet, or you can assume that the width is 1 feet. It doesn't matter. Okay, so Fr in this situation is gamma times, if we call this 10 feet h, and this one lowercase h, hc is h divided by 2. The area is h times width, but since we want to find the force in pounds per feet, per unit feet actually, we don't use it, so area is h. And you know the values, 62.4 pounds per cubic feet. H is 10 divided by 2 feet, and h is 10 feet. So the force can be found as 3120 pounds per feet. This is situation 1. Situation 2, where we have this flow. So first we should define the control volume, follow the free surface perpendicular to inflow, follow the wall, the free surface, and here perpendicular to the outflow that we have. So this is control surface 1, this is control surface 2. Here we have outflow, here we have inflow. And this is x direction, this is y direction. So for the second situation, the summation of forces in x direction equals the change of momentum inside the control volume, rho v dv, which is always 0 since we are working in a steady state in this course, plus the exchange of momentum through control surfaces, rho vx v dot n dA. So let's see what we have. You know we have this inflow, so let me erase this and also this one. So here we have we don't need to consider the friction, it's obvious, but what else we have is the pressure or the force due to hydrostatic pressure, like what we had here, Fr, and we have it on both sides, at inlet and the outlet. So here we have Fr1 pushing the flow, actually it's toward the control surface, and here we have it Fr2, again it's toward the control surface. It doesn't matter whether you have inflow or outflow. So we have two forces due to hydrostatic pressure. We have inflow at the left, we have outflow at the right, and we have Rx. That's it. So we have three forces. Let me start from here. Fr1, which is in parallel to x, and Fr2 and Rx are in the opposite direction, so minus Rx minus Fr2, there is no friction. It's equal to CS1 rho Vx in at contour surface 1 is V1. So rho times V1. V dot n, here we have inflow, so it's equal to minus V1 dA, plus on control surface 2 we have outflow, the velocity is V2. So rho, and the velocity is in x direction, so rho V2 dA. Okay, now you know how to calculate FR1. It's equal to gamma HC1 A1. HC1 equals H over 2. A1 equals H. FR2 equals gamma HC2 A2. HC is H over 2. A2 is H. Okay. Let's solve it. FR1 equals gamma 1 over 2 gamma H square minus Rx. We want to find it, minus 1 over 2 gamma H square. It's equal to minus rho V1 square A1 plus rho V2 square A2. So we can find this and this one, but we wanna and this one, but we should find V2 first. As you know, we have mass conservation, so m dot 1 equals m dot 2, or since density is constant, Q1 equals Q2. So from this we can find that V1 A1 from one of these, not both of them. For example, from this A1 V1 equals A2 V2, so V2 equals A1 over A2 V1. A1 is H, A2 is H, and V1 we have that. So V2 equals 10 over 1.5 in feet times V1, which is 4 feet per second, equals 26.67 feet per second. This is V2. Now we can find Rx. As you know, okay, let's put the values. 1 over 2, 62.4 pounds per cubic feet times 10 feet square minus Rx minus 1 over 2, 62.4 feet, pounds per cubic feet times 1.5 feet square equals minus rho, density of water, which is 1.94 slugs over cubic feet, times V1 square, 4 feet per second square, times A1, which is 10 feet, and we have to convert 1 pound is equal to 1 slug feet per feet per second square, plus the same actually 1.94 slugs per cubic feet times velocity, which is 26.67 feet per second square times 1.5 feet, and the conversion. So from this you can find Rx equals 1290 pounds per feet. So it's Rx is decreased, so we need less force to hold the gate in place. So that's it. It's the end of this tutorial. I hope you enjoyed it and you found it useful for you. So if it's the case, please share this video and tutorial with your friends, and please hit the like button and subscribe to the channel so that you don't miss our future videos. Thank you for watching. Until the next video, take care of yourselves and bye bye.